Okay, let's start. So the topic for today is sample complexity. So we will, before we spoke about online learning, part one was the goal was to present all ideas like in a simple setting without probabilities. And from now on, we will use probabilities. So we will start with realizable setting in the next 2 weeks, and then unrealizable setting. And whatever we will say will hold for all distributions over the inputs. So in October, we will speak about risk bounds that hold for all distributions on inputs. In November, we will make some margin assumption in order to get more useful results. So we will combine things. Okay, today we will say 4 things. So first thing, what was the first thing again? Okay, so I will say what is risk, what is our performance measure. Then second, I will say why do we need, so why can we only prove risk bounds on test sets under the assumption, after we make assumption on the set of true classifiers. So we cannot prove risk bounds that hold for the set of all true classifiers on some given input space. So it's called no free lunch theorem. Then I will give, and the most important part is the 4th part of the lecture, which is definition of sample complexity, and which is a quantitative definition. And before I will speak about the qualitative definition about which tasks are learnable, which sets of classifiers, for which set of classifiers can we have non-trivial performance guarantees. So for tasks, for tasks like a general model, then why we need a hypothesis class. So why can we only prove things for a limited set of true classifiers? Third, qualitative definition, and 4th, and quantitative definition of sample complexity. Okay, yes. So so let us, a classification task could be described by 2 parameters, a measure P over an input space X. Is it visible? Is it readable? Yes, I think so. So a measure P over an input space X. X will always be a non-empty set. And and the true classifier H, which maps inputs to outputs. And so a very natural measure. So if we have learned, so if we have a classifier F, how can we measure the accuracy of this classifier? Just the probability that our classifier F, so F is also a classifier. And what is now the accuracy of F? It is probability of F when we take it over a training set that it makes a mistake in the product. So for a given very specific task, this is the most natural way to classify. But normally we also have a training phase. So we select random elements for training, and this creates another source of probability. So let us sketch the 4 steps, what we will do. So first step, we will generate a training set. And here our main assumption is that training and testing is done under the same conditions. So we will use the same measure for training and testing. And so that means that we have certain symmetry between training and testing. And we know from philosophy of probability, when there is symmetry, we can infer meaningful probabilities. So first, generate a training set. So I will write it as S, and it's just a list of input, and I will always use n, small n, for the size of the training set. So in xn, according to Pn. Pn is independent distribution over n samples. So that's our second distribution. Training set are taken independently. Then we obtain, we give it to a learning algorithm. And the learning, we add labels. So we will define SH as the label training set. So it is equal to x1, h of x1, xn, h of xn. Okay, and this is given to the training set. So for this, the learning algorithm gives us this classifier. And then 3, we generate the test point according to P. Again, independently and so on. And then given this process, what could be the most natural performance measure? The first thing that comes up to you.
No, we just generate a bunch of samples and
Yeah, so the probability will be over this process, x over Pn, x over P, probability that our classifier. So, so the outcome of the learning algorithm on input this SH, I denote as FSH. And that's just probability that it's not equal to this. So this is most natural performance measure. Okay. Now, let us have some observations. First, imagine that we have two functions, f1 and f2, and they're always different labels. So we recall that we focus on binary classification. Y is equal, the size of y equals to 2. Imagine that f1 and f2 is always different from each other. Then we have that this error for f1 plus error for f2 is equal, so f1 plus probability of f2 not equal to h of x. So what can we say about this sum? It's easy quantity.
it is need value or what?
Yeah. So there is a simple value. So imagine we have two functions, f1 and f2.
One.
Yeah, it's always equal to 1, right? So for example, f1 is the constant. Imagine that y equals +1 and -1, and f1 is constant 1, and here f2 equals -2. Then one of them has accuracy at least 1/2. And so here, this measure, so the lower it is, the better. But actually, we're also happy if our learning algorithm produces something close to 1. Why are we happy here?
Because we can just do that.
Yeah, exactly. So we just invert the outcome, and then we get something close to 0. Okay. So let us do, just to get used to this definition, because there are two random things here. Let us take an example. Imagine that the learning algorithm FSH is the one nearest neighbor algorithm. And let us say that X contains 3 points, -1, 0, and 1. And that the true classifier is equal to X squared. Let us take n equal to 2. So we use training size 2. And now the question, let us evaluate this quantity. So how much will it be?
Right, so one.
Okay, it's not so easy. We need to calculate a little bit. So so we need to take, so P, sorry, I didn't say what is P. So P is uniform over the input distribution. So we need to know learning algorithm, the true classifier, and P uniform over X. Okay, so then we need to make, so to calculate this, let's make cases over the training set. So if, let us say that so S can contain 2 elements or 1 element. So it can happen that S takes 2 elements, but we can have 2 times the same element, right? So let us look to size of S equals to 1. What can we say about the error of this function? So let us say we have -1, 0, and +1. We have y equal to 0 and 1. And so the true classifier will be 1 here, 0, and 1 here. So this is the true classifier. Imagine that we know 1 point, then we will be right. What will be the accuracy? So if S equals 2. Okay, S is actually a list, not a set. So the word training set is a bit confusing. So, but imagine we received 2 times -1. What can we say about the accuracy of S of H?
No,
So yeah, 1/3.
no, I mean.
Probability to make a mistake. Yeah, yeah.
Mistake.
So it will be wrong only when it has 0. So probability over of x x not equal h of x is equal to 1/3. Then if we have the singleton 0, probability of error will be 2/3 because it will predict everywhere 0. And so so this is if S is equal to -1 and okay, it's a bit boring, but let's do it because when I asked it, there were no immediate questions. If S contains 2 elements, then
It's always probability one.
yeah, right. So conclusion is always 1/3, except in one case where we have 2 zeros that we can use to calculate it. So with probability 8, 9, we have 1/3. And with probability 1/9, we have 2/3. So this quantity is equal to something very close to 1/3. Okay, just to get used to this. Otherwise, people say strange things that this course is difficult. Very strange because I made it carefully so that it's not difficult. No, I am at this point it should not be difficult. Okay. So now we know the model, and I didn't write on the paper what I have to say. I hope I don't forget it. Okay, so this is a bit annoying because here we just have one true function, one probability distribution. So next step, most naive way to evaluate performance of learning algorithm. It is to make something that does not depend on the true measure and the input, on the true classifier and the input distribution. So let us take supremums as performance measure. So supremum over H and over P. And here we take all true classifiers, all measures. Okay, is this an interesting measure? Is the next question. And answer, I already announced it. Emotional there. Wil hij bierstraffen zelfs? Wat is al gedaan? It's always zero. It's always. I need to I need to press very hard. Okay, so now I will prove a lemma, and people call this no free lunch theorem. But I mean, then there are complicated papers, but there is nothing inside the paper. You don't need to be clever to write such papers, at least the ones I've seen. Okay, and what is this kind of basic lemma? So the lemma says that for every learning algorithm, we can come up for every measure P, we can come up with a bad true function that does no better in prediction than random guessing. So that's what the lemma says. So for every learning algorithm, for every P, for every measure, well, okay, for every N, what else? So there exists a bad classifier H from X to Y, of course, such that probability of FSH X not equal to H of X is bigger than. So random guessing when you receive a point that was not in the training set, because we can always remember the answers from the label. So probability X not in S. And 1/2. Of course, otherwise it doesn't work. So this is the lemma. And so why is it then? So this works for every measure P. For example, that means if we take uniform measure over some set P, then we have 1/2, 1 minus n over X. The input set. Yeah. And typically the possible values of input set, like for real numbers, it's infinite. But even if X is equal to bit strings, you have 2 to the power d, it goes up exponentially in d. So you will be extremely close to 1/2. That means if you want to prove something that holds for all true functions, you cannot prove something that's better than random guessing. So your optimal classifier will just randomly guess. Or you can output the constant 1 or the constant 0. So you can check the training set and output one of the two constant functions. And then you will be also as very close to 1/2. I mean, you will always, okay. It's not completely obvious. You need some measure concentrate. Okay. So let us prove this lemma. So how does it work? So it comes from probabilistic method. So it means that we will say that we will generate H randomly. And then we will show that this inequality kind of hold an expectation. So I didn't write, but here X is taken from P and S is also taken from Pn. And here the same. But I hope it was good, right? Because we are discussing this thing. Okay, so let us fix S and some X that's not an S, and then generate H uniformly randomly. So what it means, for every input, we pick a random label, one of the two labels. Okay, then let us look to the probability for this random H that FSH of X is not equal to H of X. So how much is this probability? Okay, what is happening? Our learning algorithm, it retrieves the set SH, you know the labeled set here. But how do we get these labels? We just flip random coins from x1 to xn. And then we give it a point outside S. So this test point, again, we flip a random coin. So whatever this is, this will be a random coin on the test point, but its label is independently from the training set. So it is 1/2. Okay. So now let us just take, okay, so it means that this is at least 1/2 times indicator function S, not in X, right? Because this is just a 1 here. Okay. If X is in S, this also holds. So I can draw this assumption. And now let us take expected value over S. And this is this inequality. So it's finished the proof.
Like in the other direction. Like X is not.
Yeah. Yeah, otherwise there's some how is it called? There's in logic this paradox. Yeah, so sets that do not contain themselves. You didn't have a logic course.
Oh,
Yeah, but I forgot the guy's name. Yeah, so the guy that was so excited he could not contain himself. Now I forgot his name.
there is a concept here.
Kant. What was Cantor?
I think,
Yeah.
well, he proved that like 2 to the power of n, 2 to the power of x bigger than x for everything.
No, it's not. But my brain somehow is not in logic mode at the moment for good reasons. Okay, so we've proven the lemma, and what it means is that if we want a mean, so we do not better than like reproductive learning. So Russell, yes, thank you. At least one educated person. Okay. So this lemma says that when we want to prove something for all classifiers, we do no better than reproductive learning. The only thing we have to do here is remember the training set. Okay, so first and second part of the lecture is finished. Now let's go to more serious things. And so now let us define learnability on average for a set of classifiers. Learnability on average, its name I made up for this course because I wanted to start with a qualitative definition. So, okay, I think I can just erase everything and write down the definition. So what we will do, basically it's easy. What we will do is we will restrict H to a set of, we say that the set of classifiers is learnable on average. If we look to this, if we take the limit of the supremum, but for H belonging to the class, and we want this limit to be 0, then we say it's learnable on average, otherwise it's not learnable on average. Let me write it with me. H. So that represents a set of all functions from x to y with this power. Have you seen it before? Yes. Okay, good. And so a subset of functions from x to y is learnable on average. If here, if there exists a learning algorithm such that the limit for the training size to go to infinity of supremum over H inside the class of H, and the measures P of probability that S is from Pn, X from P, that F of H of X not equal to H of X is equal to 0. Okay, so let us consider 3 simple things. Imagine that the size of the class is equal to 1. So H contains only one element. Then it's learnable on average, because what will the learner algorithm do? It will ignore its labeled training set and just outputs whatever H says. So then it's easy. If H equals 2 elements, G and G tilde, and they're always different, G and G tilde, differs from G tilde of X for all X inside the input space, then it's also learnable on average, right? because as soon as you see one training point, you know the value of all others. You know whether you're dealing with G or G tilde. So in this case, this probability, as soon as S equals 1 or more, this probability drops to 0 for just a simple learning algorithm. Okay. Now, how can we prove?
I'm sorry.
Yeah.
We have what about the sets of y and x? Are they fixed or what?
Yeah. So X is always fixed. So H is a subset of a fixed X and Y.
But if n tends to plus infinity with an like with high probability, no all the inputs. I mean, like all the inputs are contained in our set S.
So if X is finite, you are right. If X is finite, then it's always, answer is always yes. Yeah. But we will use, for threshold functions, we will use real numbers.
Does it know age?
Yes. So if there exists a learn, so a fixed H that maps a fixed X to a fixed Y is learnable if this formula holds.
The learning algorithm know the class of classifiers.
Yes. So it's fixed. So after we fix X, Y, and H, we can choose the learning algorithm. Okay. So next one, if X is infinite and H contains all classifier, then what do you think? Learnable on average, yes or no?
Probably not.
Probably not. And how do you prove it?
There is probably just
Okay.
so
So
countable amounts, countable different f of FSH.
no, you're using difficult words. So my logic is finished for after mentioning Rousseau. So let me explain it. So what we have to prove is we have to find a fixed upper lower bound. I will say that for every n, I will find a true classifier and a measure p, such that we're bounded away from 0, more than 1/4. Okay. How will I choose p and h? So I will use this lemma there. Okay. So so limit says n. Then we will pick the first two n elements and choose p to be uniform distribution over this. Okay. And now you see how the argument finishes, right? So p is uniform distribution over two n elements. So this probability will be n divided by 2n, at most n divided by 2n, even a bit less because there are repeated elements in S. So we have 1/2
by 2 or 1/2.
Yeah, so we bound this by size of S divided by support of P, which is 2n. And the size of S is at most n. So we have 1/2 times 1/2 is bigger than 1/4.
Okay.
And so it's not learnable on average, this one. Okay. Yes. And now let's prove that if H is finite, then it's learnable on average. And this important technique, because we will use leave one out technique. For this, it's important for support vector machine to have risk bound. Okay, H is finite, then it is learnable on average. Okay, and so first step, let's assume H has two elements, G and G tilde. That will be our first step. But before I start explaining about it, I will tell a story about medieval king. So medieval king, imagine he receives present from a friend. It's a huge bowl with candy. But in this time, kings try to kill each other and take their territory. No police and so if he receives present from friend, he never knows if he wants to do a favor or wants to kill him. So they have food tasters. And so king's strategy is have food tester eat, randomly select 50 candies from the bowl, give it to the food taster. If he doesn't die, then he eats one. And so, okay, an opponent knows about this strategy. So he will poison an unknown fraction of candy. So opponent hopes that taster gets all good candy and the king gets bad candy and dies. So what is upper bound on probability that the king dies?
So there are in total 51 kings.
Yeah. And so an easy upper bound I will prove is 1/51 probability that the king dies. Okay, do I need to repeat the problem? Okay, so how can we get this up? You can do a little bit better, like bound e minus 1 divided by 50, but we will not bother about this. Just 1/51 is enough for everything we need. Okay, so how do we do it?
I mean, stop. So there are just 51 kings in total in the bowl.
No, there are, okay.
Oh, there is a lot.
Yeah, there is a lot.
Okay.
Actually 51 also works, but just for easy, let's take thousands of
You can
candies.
just write this file by 50 and poison this part. And
It's unknown.
And the probability that the tester dies is e to the power of minus 1 minus e to the power of minus 1.
So you
can
create
just
more poisoned
poison
candy.
You can just poison 2% of this amount.
Yeah.
And
So you're using that 2% as optimal for the opponent.
no, but I give an example for upper bound.
Yeah, but upper bound needs to work for all fractions of poisoned candies. So in statistical learning theory, we do not know what is distribution of opponent. So okay, and this is leave one out technique. So let me just repeat, then it will be extra clear. So there is a tester and he gets random 50 candies. And then if he survives, if tester, I will arrow up for surviving, then the king takes one random candy. And so we want to prove that probability that the king dies. Smaller than 1/51. Okay, and here, what do? We take 50 candies and then one more random candy. So in total, we take 51 candies. What can we do equivalently without changing distribution of poisoned candy? Take 51 candies and then randomly take one for the king. So in first step, take 51, then random one for the king. Okay, now let us look to the 51 candies. So how many poisoned candies can there be so that the king dies? So here we have all 51 candies and so on. And so if there is exactly one poisoned candy, then the king may die. If there are 2 poisoned candies, the king will never die because one of them goes to the tester. If there are 0 poisoned candies, also king doesn't die. Okay. So only in this case, king may die. And here, that means that when the king chooses a random test point among this 51, he has 1 chance in 51 to take poisoned candy. And that's how we get this bound. Okay, So now let's go back to our problem here. So here we have two classifiers, G and G tilde. And so one of them is a true classifier. And there are two types of inputs. Inputs where G and G tilde agree and where G and G tilde disagree. If they always disagree, we already know problem is easy from this point, right? If they always disagree, the problem is that sometimes they agree and sometimes they disagree. And we are in trouble if in the training set contains only points where they agree. And then the test point is a point where they disagree. So to bound this probability here, we will use the leave one out technique. So in this probability, we first generate the test set of n points and then n plus 1 test point. Now let us have n plus 1 points and take the test point randomly among these points. So the only way that here we can have a mistake is if in these n plus 1 test points there is exactly 1 point where G and G tilde differ, and this point is a test point. So here we get the bound. So the bound for this probability will be at most 1 over n plus 1.
Is it possible that G and G tilde are different on measure 0 set?
Yes, this is possible. But then we are basically in this case. It means that we have probability 0 of taking a test point where they differ.
Okay.
And so we have. Okay. So let me write it what I have proven. Probability, sorry. I have proven that whatever is h, probability that s of h of x is not equal to h of x is bounded by 1 over n plus 1. For each of the two choices. So h is G and G tilde, right? That's our question. So we want to prove that this one is learnable on average. And so we need to say that this probability goes to 0, and it does for large n, because we have bound. Should I need to repeat that? Because last year I had more trouble explaining it. So every year, knowledge of probability increases. Knowledge of English increases. Unfortunately, knowledge of discrete math seems a little bit down. So not everything. Okay, but it's not your fault. Yes. Okay, so we agree for two functions. They're learnable on average. It's okay. But you are saying, so I cannot see it. You want me to?
Yes.
Yeah. Okay. Fine. Okay. So we want to bound this probability, and so we know that S is taken from Pn and X is taken in the same way. So we have two functions, and if in S we have a point where these two functions have different values, then for every X we will be right.
Okay.
So we only have a problem if S has no functions in which the two values of G are different. Okay, so let us bound this probability. Now let's go back to this ball with candy. Here are inputs. Poisoned candy is candy where G and G tilde differ from value. And when they are equal, it's good candy. King dying means in the test point, they are different. And so there the learning algorithm might make a mistake. And so we proved that probability of king dying is at most 1 over n plus 1. Okay. Okay, cool. Now we go to the third and most important part of the lecture. I really hope I didn't forget it. Okay, very good. The sample complexity. So this is qualitative definition. Which classes are learnable if we have a large enough sample complexity? But remember from our discussion in first lecture about performance of nearest neighbor and SVM, that it's all about the rate, because you know if we have enough endpoints, nearest neighbor will classify correctly. The problem is that this rate is exponentially slow. And in previous seminar, you made a proof about this for some weird special case that exploit the center. But actually something more general is happening. Okay. So, so now that is defined sample complexity. And sample complexity will be the smallest n, such that, okay, sample complexity has two parameters, delta and epsilon. Epsilon will be a bound on the accuracy. So we want to learn a classifier with small enough accuracy. So error on test set should be smaller than some epsilon. And we wanted to get it with high confidence on the selection of training set. So epsilon and delta. So, okay, I will not write some complexity in too much space and time. So n of h epsilon delta is equal to the minimal size of the training set, minimal n, such that there exists a learning algorithm, and that for every measure p, for every h, in h, okay, I need an extra definition. So I will use like since I use a lot the accuracy on test set, accuracy of test set. So I will write I write it a bit shorter. Because I needed to know the proofs. So here I will have that the probability over the training set of having accuracy more than epsilon could be at most delta. So that's definition of sample complexity. So it's the minimal size of training set, so that for all measures and all true classifiers, we obtain a classifier with accuracy more than epsilon with only small probability over choice of training set. Okay. And so here are some observations. So if sample complexity is finite for all positive epsilon n, so H is learnable on average if and only if sample complexity is finite for all positive epsilon and delta. If no, so if for all, if this condition fails for all n, then we say sample complexity is infinite. So if no such n exists, and h epsilon delta is equal to plus infinity. And so let's go over the same cases as before.
I'm sorry, is the quanters in the right order?
Yeah.
So
Yeah.
exist before the.
Yeah, learning algorithm must work for all measures on inputs and for all true classifiers in H. Okay, so if H contains one function, then sample complexity of H. How much is it? 0, yes. Because we don't need the training set at all, we just know the true label. Okay, in this case, two classifiers in H that always contradict each other. Sample complexity will be
1.
good. And H epsilon that equals to 1. And if X is infinite and H equals all functions on X, then infinite because of the rule I just said. So it's finite for all positive epsilon and delta, even only if it's learnable on average. Okay, and if H is finite, then the leave one out risk bound will be size of H divided by epsilon delta, and you can prove it with Markov inequality. But I will not do it. I will give you a better bound now. I mean, in a minute. I will now consider infinite the H to be the set of threshold function. It's a little bit easier. And then I will give a better bound that's logarithmic in H and 1 over delta, which is better. Okay, so class of threshold functions. That is denoted by T. Okay, I will just write the normal T is a set of all functions. So we will have X equal to real numbers in one dimension, and then we have sine X minus T. Y is equal to plus. Okay, and then I will prove that the sample complexity is bounded by NT epsilon delta bounded by 1 over epsilon ln 1 over delta. And we need to round it because it's an integer sample complex. So this is the seal, right? Okay, so now let us prove this lemma. So learning algorithm will be as follows. On the learning set, we will have positive and negative examples. And the learning algorithm will output a classifier. So let us call this function ft. It will choose a threshold to be the smallest value of a positive input.
Should we multiply by size of H?
So here T is a set of threshold classifiers. It's infinite.
Okay.
Yeah. So fortunately, we do not need to multiply here. But for finite H, okay, we will have something logarithmic in size of H. Okay. So let me repeat what's the classifier. So for our training set, it will contain some pluses and it will contain some minuses. And we will use as classifier T here the smallest value of a positive example. If there are no positive examples, then we will have the all negative classifier. So basically T will be plus infinite. I don't need special cases for it. Okay. And so let us use the name S because I want to use 3 for the true threshold. That's easier to remember. Okay, so now we have to check this condition. So we need to prove this bound. It means that we need to bound this probability. And so with this classifier, so imagine that the true classifier is here. In which region do we make mistakes?
From T to this.
Yeah, from T to this. So let us call this S. And so here is the So we have to bound the probability over the training set Pn that this interval has probability P Ts should be that this is bigger than epsilon. So we have to prove that this is smaller than delta, provided n is equal to this value. Okay. So now we will do the opposite. We will work in the opposite order. Let us fix n and epsilon, and then bound the probability that we don't reach this condition.
We want to prove this for any measure on X.
Yeah, yeah, for every measure. That's statistical learning theory. For every or a huge, like not a parameterized family. Yeah. Okay.
It's actually the same as all functions, all how do we call these functions again?
Threshold.
Yeah, yes, it's like same for the set of threshold functions on from 0 to 1.
Yeah, yeah, it doesn't matter much. So I just use all functions. Okay.
And actually,
Yeah. Okay. In the notes, sorry, I used R here, so I will help you. So R is the one that we obtain, and I used S for something else. Okay, so let me define S. Let S be the largest point, such that S is the smallest value. S minimal, such that this interval here has probability at least epsilon. So S minimal, such that Ts P of Ts is at least epsilon. Okay. So now I claim that P Ts. Sorry. I claim that that accuracy is good enough if and only if S contains an element from this interval Ts. So training set contains an interval that lays here. It's sort of observation, and from this we get the bound. So just two steps. First, we say that FSH not equal to H. And well, here it's FB. Okay, doesn't matter. The true classifier is bigger than epsilon if and only if S does not intersect Ts. Okay, clear? So if there is an element in here, then we know error is at least at most epsilon. If there is no element here, it means error must be more than epsilon. Okay. And now the only thing we need to do is bound this probability. So let x1 be the first element of the training set. Probability that x1, so over p, probability that x1 is not in Ts.
Y minus epsilon.
Yeah, it is at most 1 minus epsilon. And 1 minus epsilon is at most exponent of minus epsilon. So this trick we already used many times, right? 1 plus r is at most exponent of r.
And why do you have inequality
Here? So by definition of S. So S is minimal value such that probability is at least epsilon.
It is not equal to epsilon because this measure can be discrete and
Yeah,
okay.
yeah. So I covered both cases at once.
Okay.
Discrete and continuous. Okay. And now probability that we care about. So probability that S does not intersect this thing. S intersect TS is empty, means that also x2 is outside this interval, x3 is outside this interval, and x4 and x1. So it is the intersection of independent events. So this probability is bigger than 1 minus epsilon to the power n, which is smaller than exponent minus epsilon n. Okay. And now let us recall what we have to do. We have to say that if this is equal to n, then this error probability must be at most delta. So that's the definition. Minimal n such that this condition is satisfied. So if we choose n this value, then we are good, because then we will have that this is at most delta. I don't have space on the board, but you can do it in your head, right? So n is 1 over epsilon ln 1 over delta. So when we have this minus, so the epsilon cancels with 1 over epsilon, what leaves is ln 1 over delta. There is a minus, everything cancels, and so it's at most delta. Okay, yeah. And so that means that we finished the proof. We've proven that if we choose n this value, then this condition is satisfied. Okay. So we've proven that sample complexity is at most this value. And so we are finished. Okay. And now the last thing I need to explain this lecture. It is that if H is finite, then sample complexity is bounded by 1 over epsilon. Let me just modify this. So this is just any finite H. We're not speaking about threshold functions anymore. And here we have size of H. Like this. So if H is finite, then we have this bound. If H is infinite, then this bound is meaningless. So for all H, we have this bound. It's the last step.
Why is this bound bigger than in case? So we just changed one to
No, before it was for a specific set of threshold functions.
okay.
And they have some special geometry that allows us easy proof of them.
Mm-hmm.
But also for finite H, we can also have an easy proof.
Okay.
And the proof is very similar to this. So, okay. So let us, why not? Let us speak about H with two classifiers. And let us be lazy. Let us say that one is a true classifier and the other G is just any classifier. So I already fixed, for the proof sense, let's say the first one is a true one, the second one is just any other classifier. Okay. And now we want to say if n equals this value, then this condition is satisfied. That's what we want to prove. And we actually can have H minus 1 here. It's also true. And so we have precisely the same bound as before for threshold classifiers. Okay, now there are two cases. So either G, either we have that G not equal to H is at most epsilon. And in this case, we are done, right? So I have to prove for every P and for every H, this holds. But if G and H differ by at most epsilon, this has probability 0, so we're finished. So therefore, let's assume P G not equal to H is strictly bigger than epsilon. Okay. Oh, I didn't. I completely forgot to tell what is a learning algorithm. So of course, I cannot start to make a proof. Learning algorithm will belong to a very special class of learning algorithms. So learning algorithm can be any proper consistent learner in this theorem. So what does it mean? A proper learner is a learning algorithm that always outputs a function inside the set of classifiers. So, so here's some more definitions. So FSH is proper, or maybe it's a bit strange to say it like this, but let's say that a learning algorithm is proper if for all H and H for all S, for all S in X star, FSH is an element of H. And then a learning algorithm is proper, consistent. So if it gives the same replies on inputs of the training set. So when it gives, when the test point equals an input of the training set, it will return the same label. My marker. Let's try. So that is now a small lemma. For every proper, consistent learning algorithm, let us bound the probability for every P, for every H, for every H, probability. Okay, so sorry for being boring. I've written down a little bit technical lemma that immediately implies this thing. So I said that whenever our learner is proper and consistent, so outputs a function in the set of classifiers and always answer consistently with the training set, then this classifier, then we achieve this bound on the probability that accuracy is more than epsilon beta. Okay, so after we prove this lemma, we get this thing. Is it right? It's easy for you to see, right? No, just if we set n equal to this value, if we substitute it, then this thing cancels, and what remains is delta here. So it's easy to see that this gives this. Okay. And so now to prove it, we do the same thing. So let us consider, I will not do it with 2, I will directly do it in general. So let us fix G inside of the version space. Recall what is version space. It's the set of all classifiers in H that are consistent on the training set. we need to prove. So let us. So we need to prove that for all g's in the so we need to prove that with high probability, version space does not contain a classifier with high risk. Otherwise, some proper consistent learner might pick it and violate this. So let us fix G inside of the versions. Oh, sorry. Let us fix, that's not how the proof start. Let us fix G and H that has high risk. And then let's prove with high probability it's not consistent with S. So fix G and H with probability G not equal to H bigger than epsilon. Let's say, well, it doesn't matter. We need strictly bigger than epsilon, but it doesn't matter. And now we want to know the probability that G is not in version space. So that G disagrees with H on some of the training points. So there exists X and S, that G of X is not equal to H of X. Then proper consistent learner will not select G. And then we will, at least this G, we will be fine with this. And so this probability, how can we bound it? So what is probability that G of X1 is not equal to H of X1? Yeah, X1 is the first training point. Because at least epsilon. Yeah, it is. Oh, sorry, yeah. That at least this is at least 1 minus epsilon. Sorry, at most 1 minus epsilon. So probability that first training point does not achieve what we need is at most 1 minus epsilon. Probability that all of the n training points do not achieve our goal, minus opposite for all x, these are equal, it's bounded by 1 minus epsilon to the power n, which is exponent minus epsilon n. So the same formula here. Exponent minus epsilon n. Okay, and so what remains to be done to finish the proof? Just one step. So here I set fix G. So we have to, yeah, we have to do this for all G in our class H that have risk at least epsilon. Union bound. So we apply union bound for all G, but we can drop. Yeah,
because there is one good possibility.
Yeah, yeah. There is a true classifier. We don't need to. It has zero risk. Exactly. So then we finish the proof of proposition. Isn't it right? Okay. So we finish proof of proposition, and we are actually ahead of this lecture. 8 minutes left, but there is quiz left. So